Okay, so now we're going to talk about confidence intervals and hypothesis testing for population means. As with proportions, we use confidence intervals to estimate a population mean. So suppose we want to estimate the average age of adults in the United States who are in poor health. What is the mean? If we look at our health data, after we filter out those who are in poor health, we find that only 30 of our 1,000 people were in poor health. The mean age of the sample was 58.8 years, X bar sample mean, and the standard deviation of the sample was 14.7 years. As a quick reminder, when you filter data in Excel, you need to copy and paste the desired into a separate sheet before doing any number crunching. There's complicated Excel reasons for that. Don't worry about it. The important point here is that we found a sample mean of 58.8, sample standard deviation of 14.7. Okay, so does that mean that the mean for all adults is 58 point, all adults in poor health is 58.8? Well, no, that was just a sample of 30 of them. There's hundreds of thousands, millions who are in poor health. But it's going to be close to 58.8. How close? How much variation is there? Well, we can estimate the population standard deviation as 14.7. So the sample means, going back to our sampling distribution of the mean, vary by approximately 14.7 divided by the square root of 30, the square root of the sample size. So by, on average, 2.7 years. So is our 58.8 going to be exactly on the money? No, but sample means will vary from the actual population mean by about 2.7 years. This 14.7 over the square root of 30, this is called the standard error of the mean. In general, you use sample standard deviation divided by the square root of n. So if we had a true normal distribution, then our 95% confidence interval would be centered at the 58.8, and we would take two standard deviations, two of those standard errors, 2 times 2.7, and so we'd say that the average age is 58.8 with a 5.4-year margin of error. Now, unfortunately, the situation is a little more complicated than that, because we're only estimating the population standard deviation. Remember that 14.7 that we got wasn't for the whole population, it was just for a sample. And our theory of sampling distributions of the mean depended upon knowing the population standard deviation, sigma instead of s. It's a nuisance, but it just doesn't matter that much. Instead of a normal distribution, it follows what's called a t-distribution. And for small sample sizes, it can matter. For large ones, not so much. So if we were calculating things manually, we'd be using t.dist and t.inverse instead of norm s dist and norm s inverse. And in fact, it would be even more yucky than that, because the sample size matters, and there'd be a different t.dist for every sample size, corresponding to the degrees of freedom, which is sample size minus 1. So if we were doing everything by hand, it'd be lots of little details to worry about. But we're going to let Excel do the talking for us. So we take the data that we found, take our sample mean of 58.8, sample standard deviation of 14.7, sample size of 30, put them in Excel, tell it we want a 95% confidence interval, and boom, the work is done for us. We are 95% confident that the mean age of all adults in poor health is between 53.3 and 64.3 years old. By the way, that's a pretty big margin of error, and the reason for that is that our sample size is so small. If we had a much bigger sample size, we would get a much better estimate. Here, Excel reminds us, tells us, for those who care, that the degrees of freedom is 29. This t star of 2.05, well, remember, if it were a normal distribution, we would be taking two standard deviations, or really 1.96. So it shows how things change just by a little bit, because we don't have a true normal distribution. This standard error, 2.68, that's our 2.7. That's our estimate for how much our sample means differ from the population mean. And then 2.05 times that, that's our margin of error. But the important thing is to be able to read this and see, okay, that's our confidence interval, 53.3 to 64.3 years old. And for the difference of two population means, the story is pretty similar. We have this Excel template set up. So suppose we wanted to see how much older the people in poor health were compared to the people in excellent health. So you do the filtering. For those in excellent health, the sample size is much bigger, 241 out of the 1,000. Sample mean is 41.8, considerably younger, just as we might expect. Sample standard deviation, 14.3, about the same. And again, here we're asking for a 95% confidence interval. Remember, it makes sense. You could ask for a 95% confidence interval, or, sorry, a 99% confidence interval, or 99, or a 90% confidence interval. But 95% is what we usually go for. And here we see that the difference between the ages, average age of those in poor health and in excellent health, is between 11.2 and 22.8 years. So we're 95% confident that the people in poor health are at least 11.2 years older and as much as 22.8 years older than those in excellent health. The situation for hypothesis testing is similar. For all adults in the United States, the mean is approximately 53 years. Suppose our research question had been, instead of estimating, had just been asking, doing a hypothesis test, had been asking, is the mean age more than 53? So we're doing a comparison. Is the average age of all adults in the United States who are in poor health more than 53 years? So we use the same data as before, and now we use our hypothesis testing template. And we get this, and since our alternative had been mean greater than 53, our p-value is this 0.02. And so here's our 5 steps. The null, mean equals 53. There's nothing going on. Adults in poor health look like the general population. The alternative, which is what we suspect, is that the average age of adults in poor health is greater than 53. P-value is 0.02. So that's small, that's less than 0.05. So we reject the null hypothesis. We say that the mean is not 53. We're rejecting that, so our conclusion in plain English, we have evidence that the mean age of US adults in poor health is more than 53 years. And why did that p-value lead to that conclusion? Well, if the mean age of adults in the United States was equal to 53, sorry, if the mean age of adults who are in poor health was equal to 53, we need to go back and put that in, poor health was equal to 53, then the probability of getting a sample mean as large as we observed in our sample, 58.8, would only be 0.02. In other words, our observed data would be very unlikely to occur if the average age of adults in poor health was really only 53. The data we got, 58.8, would be very surprising if the adults in poor health was 53 years old. The average age was 53. And for 2 population means, the story of the difference is similar. Here, sample 1 is those in poor health, sample 2 are those in excellent health. The p-value we get here is essentially 0. If we took it to more decimal places, it wouldn't be exactly 0, really. It's never exactly 0, but it just means to 3 decimal places it's 0. And so the conclusion is, if the adults in poor health and excellent health had the same average age, it would be basically impossible to get sample means this far apart, which shouldn't be surprising when you look at what the sample means are, 58.8 and 41.8. There's a 17-year difference between them in the samples. It would be very, very surprising if that was just due to chance. So we'll get practice with these, but this is the theory.